Hello. So, welcome to another example again. So, in this particular example, it's on electric fields as well, right? So, what we're given here is two charges. They are fixed on a straight line. So, we have charge A and charge B, right? And then charge A is at x is equals to naught, and then charge B is at x is equals to plus 0.5. So, the way you can think about it is, imagine if you have a Cartesian plane, right? Something like this. Just a normal Cartesian plane where you have your y and you have your x, right? So we don't care about the y right now. We care about the x. So what they're saying is the first charge, okay, let me actually change color and make them red so you can see them, is here at 0. This is the origin, is it not? So it's at the origin, right? And the second charge is a distance away from the origin. Since it's plus, it means it's on the right, because you know when you go to the right of the x-axis, we are talking about positive, right? So another way to think about it is that charge A is your reference point, and you measure a distance from charge A to charge B, right? If you remember grade 10 reference points. So right, so if this is 0, this point is at 0. Actually, let me reduce. Okay, let me just make the y like this, just a dotted line. So if this point is at 0 and this is at point 0.5, we know that therefore the distance between them has to be 0.5. This distance has to be 0.5 meters, right? Because it's a simple Cartesian plane. So now these are the charges that were given, and we are told to find the net electric field at the midpoint between the two charges. Midpoint, it's the middle, the center of whatever distance you are given. So if you have a straight line like this and it has ends here and here, the midpoint is the center of the straight line. So what's the center distance of 0.5? So that distance, midpoint of 0.5, would be 0.5 divided by 2, which would give us 0.25 meters. So what this tells us is, since they said the net electric field at the midpoint, it means our R would be equals to that midpoint. So our R in this case, it is not necessarily 0.5, but it's now 0.25 meters. So that's what our midpoint, or rather our R, is. Right, so that's one thing that you had to make sure you understand very well there. And then from there, everything else is just straightforward. So now what we want to do, right, is find, firstly, the electric field due to charge A at that midpoint. So let's call this, okay. So the electric field strength due to charge A at the midpoint, right? Let's call it E1. So we know that E1, even EA is fine. It's all up to you. E1 for me means the electric field strength due to the first charge A, which is charge 1. It's the same thing. Doesn't matter really. I like numbers rather than alphabets when it comes to such things. So K, Q over R squared. So this can be QA. It's up to you. And then we have 9 times 10 to the 9th, right? And then our Q we are given to be 5 microcoulombs, and 5 microcoulombs is the same as 5 times 10 to the minus 6. And then our R is 0.25, all this squared. So I get 0.72 times 10 to the power 6 newtons per coulomb. Right, so if I place a positive test charge at the midpoint, relative to charge A, where would it go? It would be repelled to the right, right? Because charge A is positive, so it would be repelled to the right. So therefore, I can say right. So that's how you decide the direction always of the electric field. You just imagine what would happen to a positive test charge relative to whatever other charge that you want to decide the direction of or against, right? So this is how we would know where the electric field strength is going. So now that we have the electric field due to charge A, let's find the electric field due to charge B. Right, so same thing, we call this E2 KQ, let's say it's KQB, right, just to distinguish between the two. 9 times 10 to the power 9, and you take this, our R is the same, 0.25 squared. Right, what do we get? I get 0.288 times 10 to the power 6 newtons per coulomb. Same story. Now we want to decide in which direction is this electric field. So again, we come here. So QB is negative, right? If we were to place a positive point test charge here, a positive one, where would it go? It would be attracted to QB, which is still to the right, fortunately for us. And QB would also be attracted to this test charge, right? But now we are concerned with the direction of the test charge. So therefore we know that the direction of the field produced by B is to the right. Right, so that's how you do it. And then at this point, we are ready to calculate the net electric field. Remember, net electric field, you can write it as E net. That's where you basically sum all the electric fields that you have. It's important to consider direction as well. So you can either choose right or left as positive. So let's say we choose right as positive. What that means is anything opposite this direction that we have chosen will be regarded as negative. Let's start with E1. E1 is to the right, so we put it as positive. It's 0.72. E2 is also to the right, fortunately, so it's going to be positive 0.288. All of this times 10 to the power 6. Remember, mathematically I'm allowed to do this. You could have done it by just taking this whole thing and putting it here, but nonetheless you'll get the same answer. Right, so 0.288 plus 0.72 is 1.01 times 10 to the 6 newtons per coulomb. Now, since this is positive and we chose right as the positive direction, therefore this is to the right. If it was negative, we were going to say it is to the left, right? So that's how you decide the direction of the electric field, including the net electric field. So if, let's say, we were adding these, the E1 and the E2, and we find the final answer to be negative, we wouldn't leave it as negative. We would instead, after writing the negative, we would then change it and say 1.01 times 10 to the 6 newtons per coulomb. But since it's negative, we wouldn't say right, we would say left. Why? Because remember, we chose right as the positive direction. So if it's negative, it means it's going to the opposite direction, which in this case would have been to the left, right? So that's how you would have done it in that regard. All right, that's it for this video. See you on the next video.